Hello, I'm Will Roper. I'm a first year PhD student at the University of Sussex, and in this talk, I'm going to detail the merge graph algorithm, MEGA. So I do need to precede this with a quick disclaimer. So this isn't explicitly a high redshift talk, but it's about tracking the structure formation. So that's all times, and it has implications for uh, both cosmological simulations and also semianalytic models at high redshift. And hopefully I'll be able to show that in the results I'll show later on. So in this talk, I'm going to sort of briefly detail the paper that was published in Monthly Notices earlier this year. And that paper can be found at the bit.ly link I've put on the title slides here. So without further ado, I'll get into the bulk of the actual talk. So first off, just a quick primer of so what is a merge tree and a merge graph, in case anyone needs to know. So in the simplest terms, merger trees and indeed merger graphs are the family trees of dark matter halos. So they track the temporal evolution of dark matter halos through multiple snapshots of the simulation. So these dark matter halos are part of the dark matter skeleton, which we believe forms the large-scale structure of the universe. And within this skeleton, there are dark matter host halos. These are the halos that contain clusters of galaxies and groups of galaxies. And within these host halos, there are areas of higher overdensity, which are the subhalos that are the containers for galaxies. So we can run n-body dark matter simulations, or indeed full hydrocosmological simulations, and we can track the structure formation by extracting dark matter halos and linking them into trees or graphs. These trees or graphs can then be fed into semianalytic models and used to model galaxy evolution in that context. So here's just a quick schematic of that in case it was necessary. You get all your snapshots from your embodied simulation. You run your halo finder or structure extraction algorithm to identify the halos. You then link them together into these family tree-like structures, and you can then run your semianalytic model using those as an input. And here is just a L galaxy's light cone compared to the Hubble Ultra Deep Field. So that's great. We have these structures, they're widely used, but in 2013, the Sussing Merger Trees Comparison Project was run, and this was a project that took 10 merger tree construction algorithms and fed them the same halo catalog, defined using AHF, the spherical overdensity halo finder, and identified a number of problems that arise in all of the algorithms. So here I've just summarized some of these problems. Some of these were identified in the paper and some are more fundamental. So first off, we've got this is specific to spherical overdensity halo finders. So they found that it was often the case that you'd be tracking a halo between snapshots. So here you've got 3 consecutive snapshots in the simulation. And they observed this flip-flopping. So here you can see this red halo, all the mass that is identified to be within that halo is identified with the red circle here. And then you step forward one time step, and most of that mass has now been attributed to the halos around it. And then you step forward once again, and the mass has been reattributed to the original halo. So there's this weird flip-flopping, which I'm sure you can immediately see will give a highly unphysical mass evolution over time for this halo. But there are more fundamental issues. So if you're trying to track these halos back in time, you're walking backwards in time, stepping from halo to its progenitor, and then from that halo to its progenitor, etc., etc. And if to do this, you require that halo to have been identified. And what halo finders do is they apply these reality conditions to their halos to determine whether they're actually real. This is often just a check to see if that halo is bound. And it's entirely possible that due to a number of things, environmental effects, mergers, etc., that a halo could actually drop out the catalog. So you could be tracing a halo back in time down this red curve, and you could reach a point and there's no halo to step to. So as far as the tree is aware, that is the point at which this halo formed. But in actual fact, there was just this void here where the halo finder decided that this halo wasn't real. And if you're able to see that halo, you'd be able to actually track the evolution of this halo right back into the point that it formed. And there is also a similar fundamental property when defining halos within the halo finder, and that's the minimum mass threshold that you choose to define a halo at. This is often chosen to be 20, and you can get a similar sort of behavior where you're able to track a halo back through time, and then you reach a point where it's fluctuated below this 20 particle threshold. So as far as the halo finder is concerned, this is not a halo. But in actual fact, this is entirely possible. This was just a temporary drop. So had you been able to see this temporary drop, you'd be able to track this halo back to its actual point of formation here, and you'd get a lot more information about the evolution of that halo. So both these scenarios result in early truncation of your tree and a loss of information due to that. And in this case, possibly a very unphysical mass at which your halo formed. But there is yet still a worse issue that arises, and that is more fundamental to how trees are actually built. So dark matter halos, they merge together. That is exactly what merger trees are trying to map out. But they can also, you can also have these halos splitting apart. So you can have a situation like this, where you've got three halos that have come together to produce a single halo. And then the next time step, that halo is actually split apart again into two halos. But in a merger tree, this isn't allowed. So what you have to do is you have to decide, okay, well, which is my main descendant, which is me in the future. And you then decide this, and you choose which halo you should remove. And often this is just done as the most massive one, so the one that contains most of your particles, and you sever this connection, and you're left with a situation like this. And in doing that, you've lost information. So there was mass contributed this way by this halo, and now that's gone. That information has been lost, and that is a fundamental problem, as I will show. And this is where the main difference between a merger tree and a merger graph comes in. So a merger tree actually tracks this and allows this to continue happening, whereas a merger tree, as I said, cuts this out and leaves you with a loss of information. So in Mega, we came up with a sort of an approach to mitigate these issues. So first, we don't want to use a spherical overdensity halo finder. We want to avoid this flip-flopping in mass. So we, in first instance, apply a simple spatial friends of friends algorithm to avoid overlapping halos. We then apply a phase space step after this. So again, a friends of friends halo finder in phase space to remove spurious halos. So we don't want statistical fluff within our catalog. We then, to counteract the sort of temporary fluctuation in energy, so it could lead to a halo disappearing from a catalog, we have a slightly more relaxed realness criterion, which I'll go into in a second. And we also track these halos. Once they have reached 20 particles, we allow them to fall down to as little as 10 so that we can track them as their fluctuation around the mass threshold. So a halo must reach 20 particles, but we allow it to be less if it has previously been 20 particles. And then fundamentally, we build merger graphs, not merger trees, so we can avoid this removal of information by severing links to halos that have split apart. So I said we have a relaxed halo definition, and this is what that halo definition is. So we define a halo to be real if it has more than 20 particles, or 20 or more particles, sorry, and the halo is bound. So the energy given by these formula here is less than 0. Or, and fundamentally this is where the relaxed part comes in, the halo has had 10 or more particles in common with a halo in a previous snapshot, allowing for halos greater than 10 particles. So that means halo at some point must have, in its past evolution, satisfied this first condition, and then it can be allowed to fall below 10 particles, or it can be allowed to have unbound energy if it was real in the past. And I'll show in a minute how this improves the graphs and indeed trees that you get out of it. So if we just run the spatial halo finder, so the friends of friends in just real space, we get energy distributions like this. So here we have a number of particles on the x-axis and the ratio between the kinetic energy and the gravitational potential on the y-axis. And there is a huge contribution of halos if you do only this very simple spatial test that have unbound energies, even up to 1,000 times the kinetic energy of the gravitational potential energy. And I can tell you that in this region of this plot, there are roughly 3 million halos. So we've got 3 million possibly spurious halos. So we then input these halos into the phase space part of the algorithm, where we define from the virial theorem a velocity space linking length. And we then iterate decrementing this velocity space linking length until either the halo is torn apart and then it wasn't a real object, it was just fluff. It becomes bound, so it is now a real object. We've managed to remove particles that shouldn't have been there and uncovered the bound object underneath. Or we allow it to reach a minimum value of this coefficient alpha out the front. And if it reaches that value but still has E greater than 0, we keep it and then test if, at the stage of building a graph, we test if it's linked to anything real in the past. And if it was, then it's a real halo and it gets kept based on the halo definition. So if we run this, we can look at the exact same energy criterion, or energy plot, sorry, and you can now see there's a vast improvement. So whereas previously we had objects with 1,000,000 times the kinetic energy of the gravitational, 1,000 times the kinetic energy of the gravitational potential energy, we now have at most less than 10 times the kinetic energy, and where we had 3 million up in this region of the plot, 3 million halos up in this region of the plot before, we now only have 59. So it's a vast improvement here, and it's really, really efficient at removing spurious halos. So that's great. We now have a halo catalog. We can now just link these through time. So to link these through time, we take adjacent snapshots and link any halos that have more than 10 particles in common with each other across those adjacent snapshots. Doing this produces graphs that look something like this. So this is just a sort of schematic representation, and time is in the downward direction. So the present day is at the root here, and then the time of formation for each branch is somewhere at the top here. And I include this just to highlight this bottom region. So here in this schematic, we've got blue halos, so these scatter points in blue, which are the halos that would be identified to be in the tree, and only the tree for this particular halo at the present day. And then the magenta points are halos which are included in the graph. And the size of the scatter point is relative to the mass of the halo. So what the two takeaways from this that I want to show you is the complexity of the graph relative to the tree. So there is a huge amount of information encoded here that you are losing just by looking at the tree. But also, if you focus on the blue points in this main branch here, so the trunk, these are the most massive halos in the evolution. The tree is actually leaching mass off into the halos in the graph. So if you look to this tree in isolation, you'd see a halo that was losing mass as time increased, which just looks very weird. But if you look at the graph in its entirety, you can actually see where this mass is going. So it's actually being siphoned off into the main branch of the graph. So just headline, there is a lot more information that gets encoded in the graph that you lose in the tree. But that's great. So we have graphs, that's all well and good, but people's algorithms don't use graphs. So, and also we are comparing to trees. It would be somewhat unfair not to compare like with like. So we then went on to develop a method for splitting graphs apart into trees, but rather than just cutting links, we want to encode that information into the trees themselves from the graphs. So to do this, we basically loop through all the snapshots starting at the present day, and we identify any situations where you've got multiple descendants, and we split them apart based on the mass ratio of the descendants. So in this situation here, we've got one halo that has 1/3 of the mass of the halo in the snapshot you're sitting in, and then one that took 2/3 of that mass. And you can just assign the particles that went either way in the descendant to separate halos in the snapshot you're sitting in. So you tear this halo apart into two halos with the particles that are in the descendants. Of course, this might not be meaningful. It might not result in a truly physical halo. So we need some steps to check that. So we first split everything apart to create a candidate split halo. And then we accept these candidates if the split halos themselves are bound, or if they do not overlap with the main descendant. So in the main descendant here would be the most massive, the one with the largest contribution from this halo. So we test all of these candidate split halos in this way, and we get overlaps that are shown here in this plot. So on the x-axis here, you have the spatial overlap, and on the y-axis, there is the velocity overlap. And I'll sort of leave the nitty-gritty details to the paper. But suffice to say that any halo that is in this red region here are halos that overlap, and we cannot meaningfully split apart, whereas halos in the cyan region do not overlap, and we can meaningfully split into separate halos and take that information forward into the trees. So with all that said, that's all the method. It's probably about time I showed you some results. So here I've sort of selected 3 results from the paper. These are for the trees. So we've taken the graphs, we've split them apart using the method I just detailed, and plotted in each case the statistics. So on the left-hand side here, we've got the main branch length. So this is starting at the present day. You walk down the main branch of your tree as far as you can go until you have nothing to step to, so you reach the supposed time of formation. And what you can see in these 3 mass panels, so you've got a low mass regime, a medium mass regime, and then a high mass regime. And all these curves are the algorithms that took part in the Sussing merger trees comparison project. And all of the algorithms that took part in that project suffer, even in the highest mass cases, with halos that are popping into existence 1 time step before the present day, which is utter nonsense. You've got something with more than 1,000 particles just appearing out of nowhere. And it turns out this is due to the choices you have to make in a merger tree. So you have to break these links to make sure there's only a single descendant. And doing so leaves these orphaned halos that just appear as their own tree with no history to them. And this is evident also in the medium mass regime, but here, importantly, up here we don't see any of this. We manage to track these trees all the way back to their formation. Here we don't do so well. So these are instances where the energy criterion or the overlap failed, and we were unable to split these halos apart, which is sadly unavoidable. But the important sort of headline is that we still do better than the Sussing merger trees algorithms. And in this low mass regime, we see a sort of whole spectrum of formation times that we managed to track back to. We've managed to track in most cases slightly further back, and thus have a slightly lower number forming later. And that's just purely because we're allowing these halos to fall temporarily below the mass threshold and bounce around 20, as long as they don't drop below 10 particles. Which allows us to just track everything that little bit further. So you can see the same is true in the upper mass bins, where things were forming around this mass threshold and they were able to be tracked that little bit further because of that extra little inclusion of letting mass fluctuate. In the top right hand corner here, we have just the number of direct progenitors. So that's the number of halos that came together to make a halo. And it's basically just included to show that we are, even with this different halo definition, we are consistent with the other algorithms. We're not producing insane numbers of progenitors. And then, importantly, in the bottom right panel, I've shown the mass. So it's the logarithmic mass growth. It is the slope of the mass evolution. So any slope out here. One would be a catastrophic growth in mass, so an extreme gain in mass, and anything down towards -1 is a catastrophic loss of mass. And you can see that all the SMT algorithms are sort of roughly overlaid on one another, whereas our trees suffer far fewer extreme losses in mass and are biased towards a reasonable growth in mass. This is as shown in the Avail 2014 Halo Finder comparison paper. This is due to the Halo Finder definition. So you can see in that paper that the Friends of Friends Halo catalogs tended to have behavior like this. Although we didn't have the data to compare to, we still do better than those algorithms. But that's the trees. That's not sort of the point we're getting at. It's just worth showing that we have this algorithm and it can do better. But in fact, what we care about is the graphs. So here are the exact same plots, but this time for our merger graphs. So in the top panel, in the high mass regime, we've got the exact same behavior. We're not having any of these halos pop into existence randomly, and we're tracking them all the way back to their formation. The vast improvement comes in the medium mass regime, where before we had some halos with short main branch lengths here, where we were failing to track them properly. We're now able to track those all the way back. So that's great. The graphs have already shown an improvement there, and it's the same story as before in the low mass regime. The improvements are driven by the lowered threshold of the number of particles and allowing things to bounce around. Now, in the top right-hand corner, rather than plotting the number of progenitors, this is the number of direct descendants. So this is just to illustrate how much information you can lose by only selecting a single descendant. So first off, there are a number of halos that disappear, so they have 0 descendants, and their main branches end prematurely. But there's also this spectrum of much larger numbers of descendants, all the way up to, if I remember correctly, 43. So if you're ignoring these in a tree, you're losing a lot of information. And then down here in the bottom right hand corner, I'm showing the logarithmic mass growth again, so the slope and mass evolution. And here I'm just comparing one of the SMT13 algorithms, which are the red curve here, against the trees I showed previously, and also our merger graphs. And you can just see the same story is true here. So we've got even more decreased catastrophic losses of mass, and an even greater tendency to moderately grow mass. And we have completely removed this tail of extreme growths of mass that you see in the trees with Mega. And that's almost it. So I've shown the statistics from these trees and these graphs, and they look great. They're an improvement over the other algorithms that participate in sussing merger trees. But that's not an application. So where does the power of using a graph come in when it comes down to actually doing some science with it? So to do this, we calculate the baryon fraction. And you do this by, at the point of a halo's formation, you take the cosmic baryon fraction times its dark matter mass and give it that much gas, or baryon, sorry. And then you evolve it, and then you step forward in time and you take the baryonic mass given to you by your progenitors, and if you need to top up to the cosmic baryon fraction, you do so. And you track this forward to the present day. And what's plotted here is the baryon fraction of Z0 halos, and for all the algorithms in SMT13 and the trees and graphs produced by Mega. And what should immediately sort of strike you about this plot is all of the trees, including Mega, produce halos at the present day that have baryon fractions that baryon masses that are equal to their dark matter mass, which is nonsense. So I sort of just want to point out that Mega is in fact still the Mega trees do best here out of the different tree algorithms, with only a single 2 halos which exceed the baryon the dark matter mass and baryon mass. But some of the other algorithms show even all the way up to 10 times as much baryonic mass as dark matter mass, which is obviously nonsense. And then I wish to draw your attention to the graphs curve here. So this is the mega graph curve. And because we're encoding exactly where the mass is ending up when halos split apart, so you always know how much mass is going where, you're able to actually track this baryon fraction based exactly on what mass is being given to what halo. So you see a vast improvement here, and we'll be working in the future on applying this to a semi-analytic model to actually use a graph to show the improvements that can be gained by a semi-analytic model from using a graph rather than a tree. And that brings me to a close. So I just basically want to say that Mega in itself is a powerful algorithm, both on the halo finder side and the actual merger graph construction side and trees. But it's also just a statement to say that merger graphs provide a lot more information about the evolution of dark matter halos, and thus they solve a lot of problems that you can get from the nature of constructing a tree. They eliminate extreme mass fluctuations and remove the temporary loss of massive halos due to, well, Mega does, due to this relaxed condition on the halos reality condition. And we then take the information that we encode into our graphs and vastly improve the trees that we pull out of it. Although they are not perfect, due to being able to encode this multiple descendant information, they vastly improve on not using that information at all. And just a quick note on some future work. So there's an amount of probing that needs to be done on the parameter side for the phase space iteration, where that iteration starts and where it stops. And there is also a task-based parallel implementation using MPI of Mega that is currently being developed. It is almost done. There is a work in progress version available on my GitHub. And then beyond that, it will be a case of including stellar, gas, and black hole particles in the Halo Finder for use with cosmological simulations. Thank you very much for listening to my talk. I hope that you find it interesting and will read the paper. And I hope I haven't rambled too much.